I'm very happy to be with you all today to tell you about some of our work in how humans build models of the world. And I'm really excited to give this talk in support of all gender minorities in data science, including cisgender and transgender women, transgender men, and gender fluid and non-binary people. So first I want to start with the question of what is knowledge? From Henri Poincaré's 1905 Science and Hypothesis, he writes, "The aim of science is not things themselves, as the dogmatists in their simplicity imagine, but the relations among things. Outside these relations, there is no reality knowable." And John Dewey, in his 1916 Democracy in Education, writes, "Knowledge is a perception of those connections of an object which determine its applicability in a given situation. Thus, we get at a new event indirectly instead of immediately by invention, ingenuity, resourcefulness. And ideally, perfect knowledge would represent such a network of interconnections that any past experience would offer a point of advantage from which to get at the problem presented in a new experience." So what these two quotes indicate is that knowledge is a network of some kind. And not only is it a network, but it's a network that can be and is learned by example. So suppose that I must translate 15 ideas to a class here at Penn, and those 15 ideas are indicated on the left-hand side. They're related to one another in a heterogeneous way, so idea 8 is not particularly related to idea 3, but idea 8 is related very tightly to idea 7. So their relationships create a network. My challenge as an instructor is to translate this network as information linearly, because time is one-dimensional and unidirectional. So how do I create this information time series in a way that maximizes learning? Let's put that in pictures to make it a little more concrete. So on the left-hand side, I imagine the brain of the speaker or writer. There's a network of knowledge inside of their head, and they have to map that network into the one dimension of time by stringing concepts out so that they say one word after another or write one line after another if they're writing. And they need to do that in such a way that the brain of the listener or reader, over here on the right-hand side, can optimally reconstruct what that high-dimensional object was, that network. So how do we do this? How do we choose how to map a high-dimensional object into a one-dimensional space? And how does somebody who's listening reconstruct from 1D information something that's potentially higher dimensional? It's amazing that this actually happens. And I've framed this as a problem of communication in a classroom or in writing, but actually the very basic capacity to infer patterns of pairwise dependencies from incoming streams of data is what allows we as humans to learn language, to segment visual events, to parse tonal groupings, to parse spatial scenes, to infer social networks, and even to perceive distinct concepts. So it's something that we as humans do all the time, but it seems a bit like magic. So how does it happen? In order to understand how it happens, we need to build a laboratory experiment where we can show people information on a given network architecture and ask how they learn it. So the way that we do that is that we begin by allowing each node in the network to be a specific stimulus, a word, an image, or a movement. And then we allow every edge inside of the network, or one of these lines here, to indicate an allowable transition between two nodes. So I can move from idea 8 to idea 7 because those two are directly related, but I can't move from idea 8 to idea 3. That would be a non sequitur. Now what we do is that we construct a sequence of these stimuli by taking a random walk on this graph. So we could move from idea 8 to idea 10 and to 11 to 12 to 14 to 15, etc. We walk through this network, and that creates this time series, this information time series, one unit after the other. In order to see how well a human is learning the network, we ask them to perform a small task and we measure their time to react. And that allows us to see how well they are learning the network. If they respond quickly, they're learning it well. If they respond slowly, they're learning it less well. So what do we already know about this kind of problem, humans learning networks around them? Well, from the work in statistical learning and the study of artificial grammars, we know that humans are very sensitive to what are called transition probabilities. So if you're sitting in an environment where event A transitions to event B 75% of the time and transitions to event C 25% of the time, then whenever you see A, you'll expect B 3 times more than you expect C, and you're just very good at doing that. Now, an interesting corollary to that is that if you are in an environment where A only ever has 2 possible outcomes, you'll expect them both 50% of the time, and you'll be fairly confident and certain in what's happening in your world because only 2 things ever happen. But if you're sitting at A and in your environment, 3 outcomes sometimes happen from A, then you'll expect each of them 33% of the time, and you'll have less certainty. You have to prepare for 3 different possible outcomes rather than just 2 possible outcomes. You don't know which to expect most, and so you'll respond more slowly. So in simple environments, you'll respond quickly. In more complex environments, you respond slowly. So we can see this by showing humans information presented on many different kinds of networks with different amounts of local environmental complexity. And what we find is that when humans are sitting at a point in a network where there's only one possible outcome, their reaction time is really swift. In contrast to what happens when they're sitting at a place in their environment where there are 14 possible outcomes, their response is very slow. And we can plot these data points along a line here, and that line indicates to us that humans are processing 1 bit of information in 32 milliseconds. And that, I think, is just sort of fascinating that we take such a short period of time to process 1 bit of information in our environments. But it also more generally indicates that humans are very sensitive to local environmental complexity and respond in kind. But it seems that humans are not just sensitive to local environmental complexity, they're also sensitive to the shape of their environment. And to show you that, I wanted to illustrate for you 3 different kinds of networks that we've had people learn on: a modular graph, which you're seeing on the left-hand side, a lattice graph, which you see in the middle, and then a random graph, which you see on the right-hand side. And what we find is that humans respond most swiftly to the modular graph, respond less swiftly to the lattice graph, and even slowest to the random graph. And so together, those results suggest that humans process information beyond entropy or the sort of environmental complexity locally in their world, and in a manner that depends systematically on the shape of the network or the network's topology. It also suggests to us that perhaps there are some networks that we could and should be using for more effective communication. For example, this modular network, which seems to be quite easy for humans to learn. Now, to motivate the next little bit of this story, I wanted to read you a passage from Arthur Benson's Ruskin, A Study in Personality, where he says, you know how most of us in idle moments, or perhaps even more in moments when we are officially supposed to be occupied, lapse into a reverie in which a stream of thought, it may be placid, it may be vehement, sweeps through the brain from the flushed reservoir of the mind. Suppose you check yourself suddenly in one of these reveries. Try to put down in words what you have been thinking of and as you thought it. You will find it to be ludicrously impossible. Half the thoughts have passed without clothing themselves in any vesture of word. One thing has suggested another, often enough by some trivial similarity of superficial form. The whole thing is evasive, elusive, and irrecoverable. So what is happening in humans' minds as they are performing one of these sort of network learning experiments and building a model of their world? Is it something where they are very accurate, or do they process information in a bit of a haphazard way, with some pieces of information flowing past them without being recognized and other pieces of information becoming central to their model? To answer that question, we want to think about what's happening in the human mind as they're seeing the world. So here is a human who's experiencing the world as some series of events, and in order to build an expectation or an understanding of the network around them, they have to both acknowledge what's in front of them, so the stimulus x at time t+1, but they also have to remember what happened immediately prior, so this x of t in red. If they can remember what immediately happened before and see what's currently happening now, then they understand which events follow another. They're understanding the transitions. And this is somebody who has a relatively accurate memory. But we're not all perfect, and some of us may have more of a fuzzy memory, or have an error in memory, a distraction that takes us away from the current events around us. And in that case, we may remember something in the far distant past as what just happened, and sort of not have encoded anything that happened in the recent past. So this is what we would call an error in memory, or a fuzzy memory. And what we posit is that humans attempt to do 2 things. They attempt to have an accurate model of their world, but that requires high computational complexity. And that sort of trade-off, how can I maximize the accuracy of my model but use as few resources mentally as possible, creates what's called free energy model of people's internal representations of their events. And people may perform this trade-off differently. Some people may prefer more accurate memories and allow themselves to use a lot of mental resources, and others may prefer less accurate memories, allow themselves to use less mental resources. So let me give you sort of a picture of what that means to complement the little bit of math. So here's a person who has no memory, and they're minimizing mental resources and creating models of their world. They anticipate that anything in the past could have been the precursor of what they're currently seeing, and so they build a model of the world that's a fully connected network. Any event could lead to any other event. I want to contrast that with a person who has perfect memory. So their memory of the past is a delta function just on 0, which happened right before. This is a perfect memory, but it also maximizes mental resources. Their understanding of their world is completely accurate. They build a perfect model of their world. And then there's a person in the middle. This is somebody who has fuzzy temporal memory, where they remember things in the past not perfectly, but they tend to remember something recent as what's driving what they're currently seeing, rather than something in the far distant past. In this case, the humans have a fuzzy version of the true model of the world. In other words, they never really see the truth, but they see something that's close to the truth. And this poor memory person is the person who we actually see most often in our experiments. The large majority of people fall into this middle bin. Very few people fall into the no memory bin or the perfect memory bin. So most people never really see the world accurately. They see it in a fuzzy way. So obviously, once you've built a theory like this, you want to estimate the parameters from data, validate the mechanism, and then use the theory to make a prediction about a new experiment. We do all those things in the paper, which I've noted at the bottom of the slide, and they help us to understand why humans prefer this modular network instead of the lattice or the random graph, and they provide a lot of insights into how we can better fine-tune our communication with one another to maximize learning. But I wanted to leave you with one last big idea, and I wanted to motivate it with Joseph Glanville's The Vanity of Dogmatizing, which he wrote in 1661. And in that book he writes, "But how is it, and by what art, doth the soul read that such an image or stroke in matter signifies such an object? Did we learn such an alphabet in our embryo state? And how comes it to pass that we are not aware of any such cognate apprehensions? That by diversity of motions we should spell out figures, distances, magnitudes, colors, things not resembled by them, we attribute to some secret deductions." And from this passage, it makes me question is, how is it that we use our soul to read that such an image or stroke in matter signifies such an object? What images and strokes do we use? We use symbols. We use letters. We use sounds. We use movements of our bodies that create symbols that communicate with one another. How does that all happen? How do we recognize that these symbols in writing or in movements mean something? And I think that motivates a question of how do we actually use communication systems between ourselves? How do we perform information processing with the real networks like language? And so to answer that question, we moved into studying a few common examples of human communication systems to ask whether these simple laboratory experiments provide us with some insights into how humans actually communicate. And we studied in this context language networks, which were word transitions in Shakespeare, Homer, Plato, Jane Austen, William Blake, Miguel de Cervantes, and Walt Whitman. We also studied social relationships as a very important conduit for communication. And we did that through studying Facebook architecture, some science social networks in high school relationships, adolescent health, jazz clubs, and karate clubs. And then lastly, we studied a set of communication systems through music. And in this case, we're studying note transitions. So how does one note transition to another note? And what is the architecture or shape of that note transition system? We do that with works from Michael Jackson, from the Beatles, from Queen, from Toto, and then from several different classical pieces from Mozart, Beethoven, Chopin, Bach, and Brahms. And the question that we're trying to ask is, how much information are humans perceiving from these communication systems? And we break it down into two pieces. The first is they're perceiving the entropy or complexity of the system. We talked about that earlier. How complex is this network, both the local environment and the global environment? But also, now that we know that most humans don't really ever see the truth, they see some fuzzy model of the truth, we want to know how divergent the human's perception of the network is from the true network. And our hypothesis is that human communication systems likely minimize the discrepancies between the truth and what humans see. In other words, their architectures are constructed in a way that's forgiving of human biases. So is that really true? Well, to walk you through the data, what I want to show you here is along the x-axis, the entropy of the real system, and then the entropy of a random system of the same size. The gray line that you see here along the diagonal is the unity line, so that means that you would have the same amount of entropy in the real network as in a random network. What I want you to notice is that all of the colored data points are below the unity line. And what that means is that all of these communication systems have more entropy than expected from other random systems of the same size. And that makes sense. These are systems that are designed to communicate large amounts of information from one human to another human, or from a collection of humans to another collection of humans. So packing in a lot of information is sort of par for the course here. Now I want to draw your attention to the right-hand side of the slide, which is the discrepancy or divergence between how humans would view these networks and their reality. So how distinct are these two? Along the x-axis is the divergence of the real system, and then along the y-axis is the divergence of a random system of the same size. Again, the dashed gray line along the center is the unity line, and all I want you to notice is that all of the colored data points are above the unity line. And what that means is that all of these systems have less divergence between the truth and our perceptions than would be expected in a random system of the same size. In other words, these systems are relatively forgiving of errors in human memory, fuzzy temporal integration, and other related biases of perception. Interestingly, each of the systems differ in how well they do that. So this is the exact same data I showed you on the previous slide, but just reorganized so that you can really see what's different about language as compared to music. As you can see on the left-hand side, where language is in these blue colors, it has a lot of entropy, the most entropy of any of the systems that we studied. In other words, language has extensive complexity. It packs in a ton of information into a short period of space, meaning time. And contrast that with music, which is over here on the right-hand side in the purple colors. And what you can see in music is that the amount of entropy is actually quite low. What that means is that there's less information there. And we think that that's perhaps the case because music is used as an entertainment system as well as a communication system, and that entertainment may be easier or more enjoyable if it has less information content. We can also notice that the music networks tend to have more divergence from expectations than the language systems. And what that could indicate is that there's a lot of surprises in music, a lot of novelty. And perhaps that's something that's important for entertainment systems and less important or less useful in language systems. So these differences between our communication systems, I think, are interesting and motivate future work in this area to understand why different communication systems might show these differences in complexity as well as in the degree to which they are forgiving of our human biases. So with that, I'd like to summarize what we did over the last few minutes. We first learned that humans can learn the architecture of networks underlying continuous streams of information. And humans display expectations about the network that diverge from the truth, but allow them to sort of see this larger scale structure and being sensitive to whether the structure is modular or random. These biases in learning and large-scale perceptions can be explained by a poor memory or by fuzzy temporal integration. And real networks, such as language and music, fit our biases, so have low divergence from our expectations while packing in a lot of information or having high entropy. And what this set of results makes me think of is that, here we are as humans with this amazing network inside of our minds, composed of billions of neurons and trillions of synapses. This network inside of our minds is attempting to understand and learn the networks in the world around us. So in other words, it's almost as if the networks are thinking themselves. And that's reminiscent of this passage in Aristotle's Metaphysics where he says, "Mind thinks itself because it shares the nature of the object of thought, for it becomes an object of thought in coming into contact with and thinking its objects, so that mind and object of thought are the same." With that, I'd like to give you a pictorial representation of what we did over the last few minutes. We started with Hanroin Poincaré. We moved into network learning experiments. We transitioned across Arthur Benson into network learning theory, and then transitioned across Joseph Glanville into human information processing, all to help us to understand how humans build network models of our world. The work was predominantly led by Liz Caruza, who's now an assistant professor of psychology at Penn State University, Dr. Ari Khan, who's a neuroscientist, now a postdoc at Princeton, and Dr. Chris Lynn, who's a physicist, now a postdoc at CUNY Princeton on a JSMF fellowship. With that, thank you so much for listening, and I'd be happy to chat more.